Hello students, welcome to lecture 19. So in this session we will be discussing uni-junction transistor. Alright, so by the end of this session you will be able to describe the construction and working of uni-junction transistor, commonly called as UJT. Alright, so it's actually a three-terminal device. The name uni-junction transistor, it gets the name transistor because it has three terminals, and uni-junction because it acts as because there is a single PN junction. It is called uni-junction. Okay, but its characteristics, it is not. It is different from diode because it has three terminals. It is not similar to diode, and it is not similar to transistor because it cannot amplify the voltage or current. Okay, so we will be discussing what is its functionality and all. So mainly the mainly application lies in oscillator circuits. It is also used in trigger circuits, especially where you can use to trigger SCR or the triads. These UJTs are used, and it is used as a sawtooth generator and also as phase control. Sorry, here sawtooth is repeated, and for phase control applications. So this triggering circuit, when you are using UJT, it overcomes the limitation of the previous triggering circuits. So in the previous triggering circuit which we discussed are resistance and RC triggering circuits. There there is a limitation of power dissipation, and where the functionality of the trigger circuit depends on the SCR characteristics. Okay, where we have to check for the minimum required voltage and all. Right. So those limitations are overcome using UJT. First, we'll understand its construction and working, and then we'll move on to exactly how it is used as a trigger circuit. All right, how it is used in trigger circuit. Fine. So as per the construction, there is a mainly lightly doped N-type material. Okay, there will be N-type material which will have the electrical connection on each end, the ohmic contacts with the ohmic contacts, where we call this as base 1 terminal B1, and this is called base 2 terminal or B2. Okay, then there is a PN region, okay, which is embedded or inserted to the N-type material. So this P region is highly doped, okay, very highly doped, and the terminal that is across this P region is called as the emitter terminal. All right. So because of this highly doped P region in with the N-type lightly doped N-type material, there is very high resistance with the emitter open condition. All right, and because of this P and N region, there is one single junction formed. That's why the name uni junction. All right, and this N-type material, what we have here, it can be taken as interbase resistance of named as RBB, okay, where it can be split or broken up into two resistances, wherein from emitter terminal to base 2 terminal, the resistance is called RB2, and the emitter terminal to base 1, the resistance at this region is called RB1. Okay, so the total interbase resistance RBB can be broken up or split into RB1 and RB2. So generally RB1 will be shown with a arrow here indicating that it is variable, because this resistance of RB1, it can vary from 4 kilo ohms to 10 ohms. Okay, so during the operation of UJT, the resistance of RB1, it can vary from 4 kilo ohms to, it can drop up to 10 ohms. Okay. So mainly the operation of UJT can be stated as follows. When the emitter is reverse biased, we know that there will be small current flowing through. So under this condition, RB1 will be of very high value, typically 4 kilo ohms. So then we say that this UJT is in off state. All right. So whereas when emitter diode is forward biased, okay, then RB1 drops to very low value, so that the total resistance across E and B1 will be very less, allowing the emitter current to flow. Then we say that UJT will is in on condition. Okay, we'll understand that how it works. So this is the symbol of UJT, where you have two terminals, base terminals B1 and B2, okay, and one more terminal called emitter. So because it has two base terminals, this device is also called double base diode. All right, UJT is also called as double base diode. So this is the equivalent circuit where we, as you can observe, the diode here, it represents the PN junction. All right. And the arrow here, as I said in RB1, it is indicating that it is variable. Okay. So generally what we do, we connect voltage across these base terminals, which we call it as BBB. All right. And across emitter terminal, we apply the voltage VEE. Right. So always the UJT will be used in this typical configuration or the circuit, where always the B2 and emitter terminals will be positive with respect to B1. So the voltages will be always measured with respect to B1. So what you apply here, the positive potential will be always applied to B2. Similarly, at the emitter terminal, and B1 taken as a reference. All right. So the VEE will be the source, that will be a variable voltage that will be across emitter. All right. So this VEE, what we connect here, generally in typical scenario or the practical scenario, it is not the voltage source, but it will be the voltage across a capacitor in the practical scenario. Okay, that again we will discuss in the coming class. So typically the off state, if you take the off state of the UJT, observe here, the if we neglect the diode for a moment, okay, so the voltage, if you observe the RB1 and RB2, it forms a voltage divider, right? And the voltage across X, or this Vx, it is we can get it from the voltage divider, wherein it is equal to, that is Vx is equal to RB1 divided by RB1 plus RB2 into VBB, what we apply. All right. So the voltage across this point X, which we call it as eta point. All right. Eta point, which is nothing but the intrinsic standoff ratio. Okay. It is called as intrinsic standoff ratio. The potential at this point, which is given by Vx, it can be got by this voltage divider network. All right. Wherein Vx will be equal to RB1 by RB1 plus RB2 into VBB. Okay. So during the off condition, yeah, these points are the ones what I have just now explained. You can pause and observe it later. All right. So during the off condition, what happens? the voltage across this point Vx, as I said, it can be taken from the voltage divider where it is given by RB1 by RB1 plus RB2 into VBB. So this RB1 plus RB2, we can take it as the total interbase resistance RBB, okay, which is replaced here. All right. So the equation will be equal to RB1 by RBB into VBB. Okay. This ratio RB1 by RBB, it is taken as eta. This Greek word eta is ratio given by RB1 by RBB. All right. So typically its values also ranges from 0.5 to 0.8. Now, having this information about this point X and the voltage across this point, okay. Now, if you observe the voltage what we are applying at VE, that is at the emitter terminal, if it is less than this voltage Vx, all right, what happens if you observe this diode will be in reverse bias condition, right? So there is say potential drop across this RB1, which we call it as Vx now. So this Vx is some potential, right? So this VE, if it is less than Vx, then this diode will be in reverse bias condition and it does not conduct. That means there is no current flowing through, right? So that is the off condition of UJT. Say for example, if this VE, if it crosses potential, where the potential at this point is greater than the potential at this end, then the diode will be forward biased, which will be allowing the current to flow, right? So what is this condition? When VE is greater than this potential means what? Vx plus the drop across this diode, right? So when VE is greater than Vx plus Vd, Vx is what? Our potential across this RB1, right? So if the applied voltage across emitter terminal, if it is more than Vx plus the drop across diode, then the diode will be forward biased, right? Because the potential at the anode should be greater than the cathode, right? So then the diode will be forward biased, which will be allowing the emitter current to flow. And that is when we say that the UJT is in on condition. All right. So there is this potential VE, which we call it as VP, which is called peak point voltage. Okay, let's observe all these in the characteristic curve. So this is the typical characteristic curve where you can see in x-axis is your emitter current and in y-axis is your emitter voltage. Okay, typically how do we used to refer varying VE we used to take in x-axis and we used to note the emitter current in the y-axis, right? So that is also fine, but because the textbook is representing V versus VE versus IE, we will follow the same thing. Okay. So that doesn't change the operation as such. Let's understand what happens. Now, if you look at the circuit here, as I said, if this VE voltage applied at the emitter, if it is less than the Vx voltage, then the diode will be in reverse bias condition and there will be no conduction here. However, there will be some leakage current, right? There will be some small current due to minority carriers. So that is what you can observe here. There is some small current which we call it as leakage current. All right, that is observed here. So this is your cutoff region where UJT is in cutoff region, which means that diode is in reverse bias condition and it is not conducting. So UJT is in off condition. So this is the cutoff region. Once the voltage what you apply here at the emitter terminal, if it crosses the potential drop at this point, that means Vx plus Vd. Okay, so if VE is equal to VP, VP is nothing but the peak voltage which is equal to Vd plus Vx. All right, if VE is greater than or equal to VP, Okay, that is when the diode will be forward biased and there is a emitter current flowing in this point. Okay, so there is this we say that the UJT is in on condition, and there are many things that you have to understand, some important things that happens here. So as you can observe in the characteristic curve, there is a negative resistance region and saturation region. So let's see what is that, what happens. So the moment the emitter current is equal to Vp, what happens? Now the from the emitter, which is highly doped, that is P region, the holes are injected into RB1 region. Okay, the holes are injected. So the holes here, okay, the region, the lightly doped region, that is P region, uh, offers very less chance for these holes that are injected from this P region. It provides very less chance to recombine. So due to increase in the charge carriers, that is holes here that are injected, what happens? The resistance RB1 drastically drops or reduces. Okay, I'll repeat. So the highly doped P region, when you're increasing the potential, say when VE is equal to VP, almost equal to VP, then the diode will be forward biased, right? So the holes that is charge carriers are injected into this region, all right? So into that is B1 region. The lightly doped n-type material provides less chance for these holes to recombine, because of which the resistance of RB1 will reduce. As there is reduction in the resistance of RB1, the voltage Vx also starts dropping. Okay, so there is a process called regenerative, or also called snowballing process. Okay, so because of the injected holes, okay, the resistance RB1 drops, reduces. So as the resistance reduces, the voltage also drops. Okay, so this region where the resistance is decreasing is your negative resistance region. So because of the injected holes, all right, because there is no recombination taking place, the charge carriers, the injection of the more charge carriers causes this resistance to reduce. So there is a negative resistance region. Okay, so as the resistance is decreasing, what happens? More and more charge carriers are injected, which means that the current IE starts increasing, right? The emitter current starts increasing. So as you can see from this point, after this resistance decreasing, after some point where it reaches the valley point, value voltage, okay, the current starts increasing, the emitter current starts increasing. So after this regenerative or the snowballing process ends, all right, the emitter current starts increasing. So that this is the region when the RB1 will drop up to 2 ohms to 25 ohms. Remember, I had mentioned earlier and in the beginning of the session, the resistance of this RB1 from 4 kilo ohms, it can drop or reduce up to 10 ohms, right? So this is the region where we say RB1 will get reduced up to 2 to 25 ohms, all right? So that is when IE starts increasing. So this tremendous increase in the emitter current can be limited by the external resistance that can be connected across emitter terminal. All right. So now when we say that the emitter current is increasing, that is when the UJT is in on state. You say that is the saturation region. All right. So once the um, emitter current starts increasing. All right. So if you have to reduce it, or if you want to bring it back to the off state, then obviously vary the resistance that will be connected across emitter terminal, where it will control or drop the emitter current. So if the emitter current drop below this valley voltage, which we also call this point as valley current, which is nothing but similar to the holding current. So if it drops below this valley current, then the UJT will go back to off state region. All right. So this is the working of UJT and its characteristics. So this is the points are same here, what I have explained just now. You can pause and read it later. Okay. And this is a typical UJT VI characteristic curve from the textbook prescribed. All right. That is MD Singh. So it provides all the typical values. For example, if you see here, the peak voltage VP, which is equal to Vx plus Vd. Vx is nothing but eta VBB plus Vd. Okay. So for example, the voltage drop across diode, if we take it as 0.5, okay, just assume it as 0.5. If the voltage drop across the diode is 0.5, and the eta value, which I said it can range from 0.5 to 0.8, if you assume it eta to be 0.65, and the voltage applied VBB across B1 and B2, the voltage applied across the two base terminals, if it is 20 volts, then VP will be 13.5 volts. Okay. So based on that, as you can observe, as you vary VP, that is VP also varies with VBB. If you vary VBB, this peak voltage at which the UJT shifts from cutoff to saturation, okay, it depends on VBB. All right. So typical values are all given here. If you observe here, the valley voltage is 2 volts for the discussion what we have just now observed, and the valley current will be typically 5 milliamps. For such characteristic, the saturation emitter current will be around 50 milliamps. All right, and VBB, as I mentioned, it is 20 volts here. So this is a typical VI characteristic curve with approximate values. This is saturation, VE saturation voltage, okay, at which current will be saturation, that is where it reaches a saturation point. All right, go through all the points there in the presentation. We'll further discuss the application of UJT in the triggering circuit in the next session. Thank you.